bits of kit. They work very nicely in collaboration with the Bureau. Now these are a set of, as you can see, there's 5 sondes here between the 30th of November and the 3rd of December. So this is 5 successive sondes. And they're basically to show you that low down, nothing much changes. You've got about 20 parts per billion, note that, 20 parts per billion in the boundary layer. Increasing into the free troposphere, this air has been travelling from elsewhere. It's a moot question as to why you've got the maximum in ozone here. I won't go into that now. But basically, when you get into this upper region, you can see a huge amount of variability. So even though there's no variability down here, there's a lot of variability up here. And this was a period when there were these hectostorms every day. So that immediately suggests to you that what you see up here ain't a reflection of what's down there. There's no change here, and this is changing a lot. That instantly tells you there's an answer of some sort. This is a similar plot, but for the monsoon period. So these 3 first plot sondes ascents are from the monsoon period. This red one isn't. This is from a hectic period, from the break. Basically, you see same 20 parts per billion at the surface, but much more constant with altitude. So suggesting vertical mixing is quite effective in this lower part of the atmosphere. But the minimum in this part is much lower than anything that you observe at the surface. The surface concentration is very constant. And we see values here that are much lower, and we of course see values here that are much larger as well. Again, this large spread. So the question is, can we explain this? This S shape, by the way, is a common occurrence of a common feature of ozone soil profiles in that part of the world. There's a shadow station in Java which shows a very prominent S shape. So if we formulate again, we need to formulate some sort of hypothesis to look at these data. That the ozone profile in the TTL over Darwin is determined by long-range transport rather than local uplift. So that's what we will propose, that there isn't an effect of local uplift, that it is all due to uplift elsewhere and transported into this region. And if that's the case, we can use trajectory calculations to investigate. So that's what we've done. We've basically looked at the profiles, taken distinctive layers of constant concentration and run back some trajectories. These are just standard trajectories using ECMWF analysis. And we found that a lot of these trajectories ascended. As we went back in time, they dipped back into the boundary layer. So over time, they had ascended. And you kind of hold your nose and say, oh, well, okay, that means that there must have been some ascent in that region. You can ask me questions about that. But anyway, you certainly do get ascent in these back trajectories. If you take that and this plot now, which is well, clearly it's a plot of Indonesia and Australia, for a start. Now there are blobs on here. The position, for a start, the position of each blob corresponds to where the back trajectory crossed the 500 millibar surface. So they were all started from around here, and then they would go back, well in fact they might go back like that. They don't necessarily go in a straight line. So some came from the Pacific, some from here. Now the colours denote the period, so by the 4 periods that I defined earlier, so those just say when in the campaign. And finally, the numbers that are in here are the measured ozone values on the corresponding ozone sonde plot. And what you clearly see is out on the right-hand side here of the plot, we can see 4, 9, very, very low values of ozone. All the low values of ozone that we measured had trajectories that went back to here. In contrast, all the high values come from here. Now, this is a region, of course, where you have a lot of pollution in the boundary layer and ozone production from hydrocarbons and CO, the usual photochemical production. So this is not surprising that this area is a source region for the higher values of ozone and that for the lower values of ozone. During these break periods, then, it seems quite clear that there isn't a local effect. It's slightly less obvious. These blue dots are for the monsoon. Now, there are some of these that seem to originate too close to Darwin, really, to be very confident. And these values, 19, 21, and 17, are very similar to the 20 parts per billion we saw in the boundary layer. But even during the monsoon period, we saw these very low values, much lower than the local boundary layer, and they also track back to this region. So it would appear that even in the monsoon region, when you have a lot of vigorous convection, it doesn't mix this 200 to 100 millibar region in the TTL that we were looking at. And that's trajectories which didn't ascend. They show a similar sort of thing. So they don't all ascend. High values on this side and low values on that side. Intermediate values coming from the north. So the story seems to suggest that about half of these trajectories ascended and half didn't. There's a strong correlation with region of origin, which is consistent with this long-range transport hypothesis. It's more tricky during the monsoon, but even then, we can't explain what we saw by local uplift. There still must be long-range transport because you just haven't got local values of ozone that are that low, and ozone isn't destroyed that quickly. Well, we can look at carbon monoxide to see how far that's going, to see whether we can get corroborating evidence from carbon monoxide. Now these are the measurements from the egret now, not from SOM, so this is in the main outflow of the storm, and this is a flight that flew through an anvil. Time on the x-axis and concentration of CO here on the y-axis, and that's coloured in red. These green and yellow colours are cloud particle numbers. So basically, cloud penetrations, we flew in and out of the anvil basically, flew across it in this instance. And you can see a very clear correlation between carbon monoxide and cloud. First of all, well, all right, carbon monoxide is found near the ground, lift it to the upper troposphere, it'll be a tracer for upward. Well, yes and no. This is from later on in the campaign. This is in February, and now we see that the correlation goes the other way. Because by the end of the campaign, we have these very clean conditions at the surface. There was higher background carbon monoxide in the upper troposphere than there was in the lower troposphere. So once again, we can use CO as a tracer, but in the opposite direction. Unfortunately, through most of the campaign, there wasn't a huge amount of variability in the vertical in CO, and we couldn't use it as a tracer all the time, but we had enough measurements that we could. One thing that we didn't see much of was high carbon monoxide out of cloud, or low in this condition, in this period, out of cloud. So that again suggests that you can see uplifted air, but it rapidly gets mixed and you don't notice it in the background. And we play the same game of trajectory calculations on the carbon monoxide from the egret, and same sort of thing as before. And basically, what I'm trying to show here, all of these values within the green circle here have an average of 81.3 parts per billion of carbon monoxide, and over on this sector 64.4 plus or minus 2.5. And clearly they are very different and very consistent with what we got from the ozone soils. So this is, even at the main outflow level, this is, remember, not going all the way up to 100 millibars, we have that same picture. Again, very difficult to say much from these blue dots because there wasn't much of a vertical gradient at that time. Will Hayes, by the way, produced these data. Okay, I'm going to briefly skip over the next two topics. This is just to point out some work that Lorenzo Labrador has done at Manchester using an instrument built by Andreas Boltz-Thomas at Jülich to measure nitric oxide and nitrogen dioxide to look for lightning knocks. Now, everybody knows that thunderstorms have lightning in them. Remarkably, the ones in Darwin don't produce any thunder. So we're watching these lightning flickering for hours on end and you don't hear any thunder, which is quite interesting. But they produce a lot of knocks. And here we have, this is the 16th of November, the day that I showed on the previous slide actually,